In the darkness, a single cave drop trembles, carrying clues from a world the viewer cannot see. Above it, rain moves through a quiet forest, beginning the same journey towards stone and silence. Step past the entrance, and the surface noise fades into a colder, slower kind of time. Where the droplet touches stone, minerals gather in a pale bead so small it almost disappears from view. Rainwater is not pure underground. It can carry dissolved traces from soil, plants, air, and limestone. A cave may feel sealed away, yet its records often begin with weather moving above it. The first clues are not dramatic artifacts, but wet walls, stains, cracks, and patient dripping in darkness. A forest, a slope, and a hidden chamber can belong to one connected underground system of moving water. But can signals this small survive long enough to become evidence instead of noise inside stone? One falling drop opens a larger question. What else can darkness protect after the surface forgets? Inside the chamber, air barely moves, while the forest above is constantly being rewritten by weather. Thin mineral bands appear like pages, building slowly where water keeps returning to the same point. Those layers are not automatic answers. Scientists must measure, date, and compare them carefully with other records. The protected clue begins outside, in rain-touching leaves, soil, roots, and exposed rock above the cave. To understand the cave's memory, we first have to see why the surface forgets so easily. On the forest floor, nothing is truly still. Water, roots, insects, and decay keep working together. Each raindrop strikes loose soil, breaking tiny edges and starting a slow movement downhill toward lower ground. Once runoff begins, particles leave their original places, carrying pieces of context away with the muddy water. A small slope can rearrange evidence across a backyard, much like water redirecting a driveway stain. The ground feels permanent underfoot, but its upper layers are always shifting, mixing, and wearing away. Roots push through soil like living wedges, disturbing layers that might otherwise stay in useful order. Worms, beetles, fungi, and microbes move organic material, turning the surface into a living mixer every day. Scientists call this bioturbation, a simple idea life stirs the ground and blurs time in soil. Even a hiking boot can press fragile traces deeper, smearing evidence before anyone notices the change. A highway cut can reveal old layers, then expose them to rain, heat, vibration, and collapse. Once buried rock reaches open air, weather begins attacking surfaces that had been protected for ages. When a layer falls apart, the damage is not just broken stone, but lost context forever. An object moved from its place loses part of the story that once made it meaningful. Yet the same water that erases the surface can become the messenger entering a cave below. It slips into ordinary cracks, not grand openings, carrying small clues below the visible surface world. A cave system often begins with fractures so narrow they look meaningless from the surface above. Limestone hides roads inside itself, where water can follow pores, joints, fractures, and invisible weaknesses below ground. Slightly acidic water reacts with limestone, dissolving tiny amounts of rock one passage at a time. Over long ages, countless small changes can widen cracks into corridors large enough for humans to enter. This passage is not empty by accident. Water carved its route through resistant stone over time. Where the stream moves faster, it carries sand and silt deeper into the cave system below. Ripple marks in cave mud can reveal that water once hurried through this quiet floor long ago. Then the tunnel opens, and motion gives way to a chamber where time seems to slow. In still pools, fine particles settle gently, preserving order that rushing water would destroy almost immediately. A single sinking grain raises a new question. When movement stops, what begins to accumulate below? Quiet cave zones can gather sediment layer by layer, building records instead of scattering them downstream. But layers only become evidence when scientists understand how they formed. and whether disturbance changed them. Careful footsteps matter here because the researcher is walking across the record being studied below the surface. One careless touch can crush a mud edge that may have taken centuries to form intact. A patch smaller than a kitchen table can contain a slow accumulation of underground history beneath it. Brown and white stains trace older water paths, marking routes the cave no longer uses today. The reversal is simple: caves are connected to the surface, yet sheltered from its constant chaos. Fast water carries clues away, slower water lets them settle, concentrate, and sometimes survive for years. From rain to crack to chamber, the whole system works like hidden plumbing beneath the land. So when rain disappears into limestone, how does it become part of an underground archive over time? The eroded limestone does not end the story. It opens the first doorway for water to disappear below. From above, one narrow crack becomes part of a hidden drainage system spreading under the whole slope. When surface water vanishes into stone, the cave archive begins before anyone can see a chamber. In limestone, slightly acidic water can widen small fractures slowly, turning hidden weakness into underground passageways over time. Rainwater changes underground after moving through soil, where carbon dioxide helps make a weak natural acid. The acid is gentle, but given enough centuries, it can slowly eat paths through carbonate rock. Long before a person could enter, a cave may begin as a gap thinner than a finger. Tiny openings grow when water returns again and again, following the same hidden weaknesses in stone. The curves on cave walls can reveal how ancient water once turned, slowed, or surged through darkness. Before crystals or bones appear, the passage itself becomes the cave's first record of change. An empty chamber may feel still, yet its walls remember the vanished river that carved it. Old water lines and mineral stains can mark earlier cave phases, like faded notes left on damp stone. Scientists read those surfaces by comparing shape, chemistry, position, and the geology surrounding the chamber itself. A careful researcher sees more than walls. She sees a damaged map of water's older routes. But if water created these records, why are some clues preserved while others vanish completely underground? The strongest archive often forms after violent flow leaves, creating a quieter space protected from disturbance. On the cave floor, thin sediment layers settle when floods, mud, or slow water leave material behind. A few inches of cave mud can work like a tiny filing cabinet under the earth. Those small grains may connect a local storm to larger changes moving through the landscape above. The archive begins outside the cave, where rain first passes through soil, roots, and fractured rock. Before reaching darkness, water crosses a living filter of soil grains, roots, microbes, and decaying leaves. Along that path, water can pick up chemical signals from the surface world it has just crossed. Once underground, the route rarely stays straight, splitting through fractures, pores, and invisible limestone pathways below. If water takes so many routes, which path leaves a record strong enough to survive time? Fast water may carve the cave, but slow dripping often builds the records scientists can later read. When dissolved minerals fall out of water, the cave begins turning each passing drop into stone. One mineral-rich drop can connect the ceiling, the floor, and the surface into a single system. Each splash is tiny, but repeated drips can build shapes that outlast cities, roads, and empires. A formation smaller than a school bus may hold a timeline longer than any American city. Yet the cave never labels its dates, so every layer must be decoded with scientific caution. Bands inside cave formations can preserve shifts in drip rate, water chemistry, and growth conditions over time. Some layers are visible to the eye, while others only appear through careful instrument measurements in laboratories. Because these records grow so slowly, even one careless touch can damage a fragile mineral surface. Human footsteps and hands can harm the underground archive. People enter caves, hoping to understand more clearly. Protection does not make a cave less mysterious. It gives the record time to continue growing. Stable temperature, darkness, and limited disturbance can help certain traces remain readable far below the surface. A still cave pool can look like a mirror while quietly checking the chemistry above ground. When water chemistry changes, the cave may respond to storms, droughts, soil shifts, or surface disturbance. One quiet pool can link rainfall, soil, rock, and drainage across a much wider hidden area. To understand the archive, the journey has to follow water deeper into the hidden system below. The same water that builds records can erase them when floods return with sudden force underground. A cave archive survives only when delicate evidence escapes repeated scraping, flooding, collapse, or contamination over time. Some records endure in protected pockets just above the passages where violent water usually travels below. Undisturbed surfaces can reveal where recent floods have not swept the cave completely clean in modern times. A cave is not one environment, but a patchwork of active, quiet, wet, and dry zones. That patchwork decides what remains readable, what changes over time, and what disappears forever into darkness. Thin calcite curtains show that stone can grow in sheets, folds, and delicate glowing edges underground. Inside those bands, the next mystery begins. How can growing stone become a timeline we can trust? The cave archive becomes clearest when dripping water turns mineral traces into layered stone over time. How much time can one slow, growing formation hold before its layers become older than human memory? At this ceiling point, a single drip brings dissolved minerals from the forested surface into the chamber. When cave water releases carbon dioxide, dissolved limestone can reappear as tiny crystals of calcite along the ceiling. In the protected air below ground, those crystals can keep building where the surface keeps erasing. Darkness, steady temperature, and limited disturbance allow some formations to survive far longer than exposed rocks. The same drip that carved this passage may now be writing a timeline almost too slow to notice. Now the cave's story changes from hollow space to growing stone, layer by layer, in darkness. Could one thin mineral ring be the first visible page of a much older underground record? Each drop leaves almost nothing, yet thousands of repeated drops can slowly raise a formation over time. A stalagmite only a few feet tall may hold environmental changes spread across thousands of years. Beside a person, it looks frozen, but its surface is a geological notebook still being written. Colored bands may reflect changing minerals, shifting water paths, and conditions moving above the cave through time. Stone seems silent, yet these layers formed because the outside world refused to stay the same. Like tree rings, cave layers mark growth, but they answer to water traveling underground through rock. Researchers cannot read these bands by sight alone. They measure chemistry, structure, and age in detail. Because active formations are fragile, even a fingertip can contaminate a surface still growing today inside the cave. A darker band raises the archive's hardest question: what changed outside when this layer formed? A corridor of formations may share one cave, yet each drip can tell a slightly different story. Different drip points collect water from separate roots through soil, roots, and fractured limestone overhead before entering. One cave drip may begin as rain filtering through leaves, soil grains, and hidden cracks above. During that journey, water can collect chemical traces before it finally reaches open cave air below. Before taking any sample, a researcher maps the setting because context gives every layer its meaning. Loose fragments can be valuable, but they may not match the history of active formations nearby. One careless step can disturb mud, crush crystals, or damage growth that survived for centuries in silence. When sampling is permitted, A tiny core can reveal layers no visitor could see from outside. Dating methods help assign ages to those layers, turning stone into an ordered sequence through time. The sample may be small, but its chemistry can reflect changes across the landscape above the cave. The next clue is not only age, but what the water carried into darkness with it. Oxygen and carbon signals can shift with rainfall, vegetation, temperature, and cave processes through long periods. But no chemical signal reads like a headline. Each one must be decoded with patient caution. Even the quietest cave record begins in a living surface of soil, roots, and rain above. The underground archive is tied to storms and seasons that never visibly enter the chamber itself. A stalactite grows downward when mineral, rich water leaves its first traces on the ceiling above the floor. When that drop lands, a second deposit can build slowly upward from the cave floor below. Over enough time, the ceiling and floor growth can meet, forming a single stone column between them. A column may look like one object, yet it contains many separate episodes of environmental change. Photographs, measurements, and careful samples let scientists compare cave evidence instead of trusting impressions alone underground. A thicker band may suggest changing drip conditions, but the meaning depends on local cave context. Even damage can enter the archive, sealed under later mineral growth, like a buried scar in stone. In this darkness, time feels stopped, which makes the slow record feel almost impossible to imagine. To understand that memory, the journey must leave wet stone and enter the laboratory beyond the cave. In the lab, cave silence becomes numbers, images, dates, and measured chemical patterns on bright screens. Polishing the sample exposes hidden bands that the outside surface kept concealed from view for years. Age markers connect individual layers to approximate moments in the past, building a cautious timeline for comparison. Special instruments measure chemical ratios far too small for the human eye to detect alone reliably. Those ratios are clues, not final answers, about ancient water, vegetation, and climate outside above ground. A cave record can complement tree rings, ice cores, and lake sediments, filling different scientific gaps. If a sample is altered or broken, it can mislead the entire reconstruction of the past. Researchers check for contamination, missing sections, and later changes before trusting the timeline they reconstruct from stone. When reliable, the timeline may reveal droughts or wet periods older than written records in history. Now the story returns underground to ask what those ancient climate shifts actually looked like below. Inside the stalagmite, thin mineral bands appear like quiet growth lines, turning darkness into a physical timeline. Each repeated drip leaves a trace, slowly building layers that can outlast forests, floods, and forgotten surface changes. To read that record, researchers work carefully because one careless sample can damage centuries of slow growth. Instead of cutting the whole chamber apart, instruments examine tiny pieces while the cave remains mostly untouched. A fragment smaller than a penny may hold more time than many written records on the surface. The record is real, but it is not obvious. Stone must be measured before it can tell its story. Rainfall, soil, and vegetation above the cave can subtly change the chemistry carried down by each drip. The same drop that writes stone also falls toward another archive waiting on the cave floor. As ripples spread across the mud, the timeline shifts from growing stone to evidence gathered underfoot. Down here, the floor may remember things no stalagmite can, hidden beneath a skin of sediment. A pale irregular edge appears in the mud, too small to explain, too distinct to ignore. From a crouched headlamp view, every clue feels fragile, partial, and surrounded by darkness, waiting for context. A brush clears loose grains, revealing that the fragment may be bone, shell, or only stone. Its position inside the sediment may matter as much as the object itself, because context carries meaning. Layer by layer, the cave floor can build a protected page, recording events that settled into darkness. The stone timeline does not end. It bends downward, toward mud, fragments, footprints, and older visitors. Chapter 4 begins with a harder question: what else survives when the cave protects more than minerals? Across the chamber floor, mud banks, ledges, and fallen blocks create pockets where different evidence can rest. Small markers do not solve the mystery, but they preserve the relationship between separate clues underground. A shallow impression in hardened mud may be more than a mark. It could be movement paused in place. When soft mud dries undisturbed, a passing foot can remain as a quiet record of direction. Beside a measuring scale, one small track begins to suggest size, stride, and the path once taken. Before naming the visitor, researchers document shape, spacing, and setting, carefully keeping interpretation behind the evidence. The most important clue may not be one perfect footprint, but a faint pattern across the floor. Those patterns point back toward the entrance, where animals once crossed between daylight and the underground world. Modern cave animals remind us that movement, shelter, feeding, and disturbance can all leave traces behind. But a mark alone rarely tells the full story. Water, claws, boots, and time can overlap. Scientists compare depth, spacing, and edges, separating possible causes before turning a trace into a claim. Reading the floor often means leaning over fragile mud, where even balance becomes part of the work. Above the trackway, a darker ledge suggests another record, thinner and easier to misread in darkness. The dark band holds tiny black flecks, hinting at a material different from the mud around it. With tweezers and a steady hand, a single fleck enters a vial instead of a conclusion. Only testing can show whether that material records fire, contamination, plant matter, or something carried by water. Taken from its layer, the same fleck could lose the very information that made it useful. Flood mud, roof collapse, dry dust, animal activity, and human visits may all stack into one wall. A sudden flood can bring outside material deep inside, while also moving older evidence from its place. Grids turn the floor into a map, helping researchers protect distance, direction, and relationships among clues. A dark layer and a bone fragment together raise questions that neither clue can answer alone. When bone, charcoal, and sediment remain together, the archive becomes stronger because the clues support each other. Now the investigation shifts from chemical traces toward remains that once belonged to living bodies underground. A larger shape emerges grain by grain, still protected by the sediment that has hidden it. To identify a fossil, scientists compare anatomy, age, location, and the surrounding cave context before naming it. A measuring scale turns the fragment into a question of size, body plan, and possible age. The same darkness that feels empty can shelter fragile traces long after daylight would destroy them. Bones may enter through falls, predators, floods, nests, or shelter, each path leaving a different story. A visualization can suggest possible routes, but the real evidence must decide which route fits best. At a fragile site, not touching can be as important as discovering what lies in front of you. Photographs, notes, and markers capture the original positions before any sample changes the scene forever underground. One small fragment can open a larger question about vanished animals, climate shifts, or human presence. As the camera pulls back, bones and layers become one wider archive still waiting to be read. The excavation grid turns scattered fragments into a map, showing that every clue needs its exact place. A bone edge draws attention, but the sediment touching it may tell the more important story. Without context, one fragment can mislead. Science begins by asking what the cave can actually support. Before anything is moved, researchers record position, because removing one clue can erase its relationships forever. A marker no bigger than a coin sits inside a chamber shaped by ages of water. The cave floor is not just dirty ground, it can be a layered archive underfoot, slowly forming. Floods, animal traffic, and falling rock can rearrange evidence long before humans arrive with lights below. A quiet side corner may preserve a cleaner record than the wide path everyone notices first. A fragment may suggest an animal, but certainty begins only after dating, comparison, and careful context. The cave floor archive widens now, from isolated remains toward movement, shelter, and behavior across deep darkness. In a side alcove, faint depressions appear in mud, but their meaning is not yet clear. Raking light crosses the floor, revealing shallow impressions that vanish from a normal viewing angle underground. A print needs scale, location, lighting, and comparison before it becomes useful scientific evidence at all. A trail can show movement through darkness without proving who traveled there or why exactly yet. Signs of life rise above the floor, reaching into ceiling pockets stained by old roosts overhead. The chamber becomes vertical, holding possible evidence from wet mud to shadowed stone overhead above it. The archive of the past shares this chamber with animals still moving through it tonight nearby. Preserved traces give way to living motion, and the cave's silence suddenly feels less empty. If darkness protects old evidence, how can a living community survive so far from sunlight below? Nutrients carried by animals can feed entire cave communities beyond the reach of green plants outside. A cave cricket crosses the floor, where dropped organic matter gathers in small, valuable patches below. What looks like waste on the floor can become fuel for organisms hidden in darkness below. Insects, fungi, and microbes recycle scarce food, turning the cave floor into a slow living system. A food web can work without sunlight when energy keeps arriving from the outside world above. The cave is not lifeless, it is selective, fragile, and dependent on small, regular inputs from above. Researchers keep distance and low light, because even quiet observation can change animal behavior underground quickly. A single step may move dust, spores, or sediment into places protected for centuries below ground. Beyond the marked path, the living system continues into darkness most visitors never enter safely at all. Thin films on the wall may hold microbial communities invisible until light strikes at an angle. Water links wall life, floor organisms, and darker pools waiting deeper inside the cave system below. A still pool reflects stone above it, in a room that has never known sunlight directly. What changes when an animal spends generations in darkness, where daylight never reaches the body at all? A pale cave, adapted creature moves through water where touch and vibration matter more than sight alone. In permanent darkness, smell, pressure, and tiny movements can become more useful than eyes alone here. Losing vision is not failure here. In this world, it can become survival over generations underground. Creatures in these pools depend on nutrients moving through water, rock, and organic debris over time. One cave pool cannot represent every underground ecosystem spread across different American landscapes and climates today. A quiet pool may still be connected to rain falling through soil far above it outside. The same pathway that feeds cave life can also carry pollution into hidden chambers below ground. The living cave reaches upward through water, roots, cracks, and unseen roads to the surface above. A narrower passage shows how evidence and life can travel through the same hidden routes underground. Small animals follow moisture, edges, and scent trails across a floor that seems empty at first. Nutrients from animals can alter sediment, microbes, and even chemistry near growing formations nearby underground too. The archive is not untouched. Living processes can write their own signatures into it slowly over time. To read a cave record, scientists must consider biology, water, chemistry, and disturbance together carefully below. A cave can preserve the past while actively changing the very archive it holds inside itself. Careful observation matters here. because the record is fragile, living, and still forming today underground now. In some cave systems, the safest discovery begins by choosing not to step forward yet again. A film thinner than paint can matter inside a system stretching under hills and towns above. The living cave now leads toward hidden rivers, where the archive connects to a larger world. A pale invertebrate traces the pool's edge, moving quietly where faint nutrients gather on damp limestone in darkness. That tiny speck is food, reminding us cave life often begins with material imported from the world above. Without sunlight, many caves depend on water, animals, roots, and drifting organic debris for their limited energy. Microbes spread across wet stone, while tiny insects move through a habitat held together by moisture and shelter. A living film only inches wide can matter inside a chamber shaped across thousands of quiet underground years. Researchers step carefully here because some underground habitats may recover slowly after even small human disturbances occur. Darkness is not empty space. For specialized life, it can become a steady and protected home below. Living surfaces may leave subtle chemical traces, adding another layer to what caves preserve over long periods. The water feeding this pool may also point toward roots much larger than this quiet chamber. Beyond the living edge, the same trickle disappears into corridors the flashlight cannot fully reach ahead. A bat roost can feed a cave floor, dropping nutrients that support entire tiny communities below it. Around one small deposit, life gathers tightly, showing how valuable every imported crumb can become underground. Many cave ecosystems survive on small inputs, moving slowly through routes hidden from ordinary surface view. One careless step can crush surfaces that support life, record change, or grow over centuries underground. The chamber narrows ahead, and the living pool gives way to a corridor carved by water. A stream no wider than a driveway crack can help shape passageways deep below the surface. The cave is not simply a room in stone, it is part of a moving underground network. But where does this water go after it slips beyond the chamber's last visible bend ahead? Tiny suspended particles drift onward, hinting at invisible pathways between rooms, cracks, and deeper passages below. The living cave fades behind us, while moving water becomes the next clue in the underground story. Above the cave, rain begins quietly, striking leaves before its hidden journey under the ground starts. A shallow woodland depression can become an entrance, swallowing surface water after a heavy storm passes. Small cracks collect rainfall first, guiding it toward limestone weaknesses that may open below the forest. In karst terrain, water dissolves soluble rock and follows fractures, slowly enlarging hidden routes below ground. What looks separate on the surface may connect underground through passages no hiker can see today. A hole smaller than a fist can feed a corridor large enough for flowing water below. Underground routes rarely behave like one straight pipe. They split, merge, stall, and rejoin repeatedly below. A storm above can reach the cave below, changing water levels in surprising ways very fast. When stormwater enters quickly, a quiet stream can rise, cloud, and turn dangerous within minutes underground. The water keeps moving past the light, leaving one question unresolved: where will it emerge next? Researchers test these hidden connections with tracing methods, following water without entering every passage themselves directly. A harmless dye can mark the flow, revealing movement through rock that remains unseen underground nearby. The tracer does not map the whole cave. It tests whether two distant points are connected. Then the marked water leaves the visible passage, carrying the mystery beyond the camera's reach downstream. One hidden route may travel miles, even when the surface above seems completely unrelated to it. At a spring, people finally see what the underground system has carried from upstream today below. Water that vanished into one hillside can return far away, colder, clearer, and subtly transformed again. Some hidden systems run beneath ordinary roads, neighborhoods, farms, and places people rarely question daily above. That returning water can feed surface streams, wetlands, and ecosystems far beyond the cave itself nearby. If water links these places, anything carried by water may link them as well underground too. Runoff can carry soil, oil, fertilizer, or waste toward openings that lead underground after heavy storms. Sinkholes and shallow depressions gather water from surrounding land, concentrating what the surface sends downward quickly. In many karst landscapes, water can move downward faster than it would through layered soils elsewhere. A cloudy plume briefly exposes the connection, making the hidden route visible for a moment below. Sampling turns concern into evidence, measuring what the water actually carries through the system underground today. Hidden cave water is not separate from daily life. It belongs to the same landscape above. Particles and chemistry moving downstream can affect cave pools, springs, and fragile habitats along the way. The scale widens from one passage to land use, groundwater, cave networks, and spring outlets beyond. A spring may look clean to the eye, while still needing careful scientific testing nearby today. The route pulls us back beneath the surface, where climate clues are waiting in darkness ahead. The visible stream drops into a lower slot, and the cave's next route slips out of reach. From the probe's view, the flooded passage feels too narrow for a person, but wide enough for water. Thin fractures in the limestone accept the seep, turning solid rock into a hidden drainage map. A faint scientific overlay reveals branching paths, not one tunnel, but many uncertain routes through layered stone. Beyond this chamber, the water network may stretch farther than any flashlight beam can follow today. Researchers release dye into sinking water, marking a question the cave itself will answer downstream later. As the color spreads, the underground system begins to reveal a connection no surface map showed. Water that vanished here can emerge far away, under trees, beside roads, or near spring-fed creeks. That hidden link means a cave is connected to streams, habitats, and landscapes above it every day. But the same pathway carrying natural clues can also carry pollution from places no one suspects. Above ground, rain gathers on roads, yards, leaves, and fields before finding the easiest opening below. During a storm, runoff can reach sinkholes quickly, pulling the surface world straight into darkness below. One small depression in the ground may drain an area much wider than it appears from above. In karst country, water often skips visible rivers and chooses secret routes through fractured stone instead. Inside the cave, muddy pulses bring soil, leaves, and organic traces from the land above after rainfall. Small sensors watch the stream after storms, recording changes too subtle for human eyes alone to notice. A sudden chemical shift can show that surface water reached the cave faster than expected after rain. Even a clear pool may hold evidence of rain, soil, roads, farms, and forests above today. For cave life, that connection matters, because water quality from the surface becomes habitat underground too. Every storm sends new clues into the system, mixing the present with far older records below. A karst network can link caves, springs, wells, and towns through unseen underground plumbing across miles. Water beneath an ordinary neighborhood may share pathways with passages explored miles away by cave researchers. By monitoring cave streams, researchers begin to map connections that daylight never reveals at the surface. Dissolved minerals, organic matter, and chemistry travel together, turning water into a moving message underground today. The cave records the outside world because it is protected, yet never completely isolated from change. Each drip that reaches a growing formation adds a tiny layer to the underground archive over time. Minerals carried by groundwater can settle slowly, building stone records from repeated wet seasons and dry years. the story now shifts from moving water to the time it leaves behind in layered rock. The same water that feeds cave life can also feed the mineral record underfoot each day. So the deeper question becomes how scientists read a stone record written without words or dates. A stalagmite is not just a cave decoration to researchers. It can be a timeline of change. Across its surface, fine bands hint at seasons, water flow, and changing conditions above the cave. Each layer forms under particular conditions, preserving small differences that may matter centuries later to scientists. Sampling is done carefully because removing even a piece means altering a formation forever in place. In this work, restraint is part of the science because cave stone grows painfully slowly underground. A few inches of mineral growth may represent more history than an old family archive can hold. The sample leaves the cave, and the investigation moves from darkness into the laboratory light for decoding. Under clean lab light, the cave sample becomes measurable in ways the eye cannot manage alone. A polished cut reveals bands hidden inside, like pages sealed within the stone for centuries below. But seeing bands is only the beginning. Scientists still need dates and chemical meaning before conclusions. Dating methods estimate where different parts of the growth belong on a long timeline of change. Tiny samples along the growth axis help build the sequence from younger layers to older ones. Sensitive instruments measure chemical changes so small they would never appear in ordinary cave light alone. Oxygen and carbon signals can reflect rainfall, vegetation, temperature, and the cave's own conditions over time. The chemistry is not a simple calendar, and every signal needs careful interpretation before becoming evidence. Scientists compare cave records with tree rings, lake sediments, ice cores, and weather history when possible. When several archives point in the same direction, the interpretation becomes stronger and more useful scientifically. Good cave science accepts uncertainty because ancient evidence rarely speaks in complete sentences or simple answers. Every lab result must return to the cave environment that shaped it in the first place. Now those measurements can begin revealing ancient droughts, wet periods, and questions still buried in stone. The sample enters a lab where ancient darkness becomes numbers, dates, and carefully measured chemical signals. A technician labels the tiny powder because one misplaced mark could confuse centuries of underground history. Inside the instrument, invisible atoms help reveal when each thin mineral layer first hardened in place. The cave record does not speak plainly. It answers only when scientists ask very careful questions. A glowing screen turns raw measurements into a timeline, but interpretation still requires patience and doubt. Each data point is a clue, not a headline, and the strongest story comes from patterns. The stalagmite becomes less like a rock and more like a long, silent climate ledger underground. Some layers suggest wetter decades, while others point toward drier seasons above the same hidden chamber. But a cave does not record weather like a backyard thermometer or a television forecast outside. It records filtered signals changed by soil, stone, water paths, and the cave air itself over time. Oxygen signals can shift when rainfall patterns change, leaving subtle fingerprints inside the growing stone layers. Carbon signals may reveal changes in soil, plants, or the way water moved underground slowly below. No single measurement tells the whole story, so researchers compare several clues before drawing careful conclusions. The cave becomes part of a larger investigation, linked with tree rings, ice cores, and lake mud. A dry ring in a tree and a pale band in stone can point toward the same drought. When records agree across landscapes, confidence grows that the cave preserved a real environmental change clearly. When records disagree, the disagreement matters too, because it may reveal a local cave effect instead. Science advances not by forcing the archive to speak, but by learning its language slowly underground. The camera follows the timeline backward, from recent decades into centuries no human witness ever recorded. A drought that vanished from memory may still remain as chemistry inside a cave formation today. In the American Southwest, ancient droughts help explain why long records matter beyond simple curiosity today. Modern weather records are short, but caves can stretch the story far beyond written measurements alone. A monitor shows rainfall pulses, desert plants, and cave layers aligning like separate scientific witnesses together. The point is not to predict every storm, but to understand how systems changed before humans. Deep time can make modern change feel less isolated, and sometimes more serious than expected today. A researcher pauses over uncertain data because honesty about doubt is part of the evidence itself. The cave archive is powerful, yet every timeline carries margins, assumptions, and unanswered scientific questions still. Some layers grew quickly, others nearly stopped, and those pauses can be as important as growth. A gap in stone may mark drought, flooding, broken flow, or simply a rote that changed. That uncertainty does not make the record useless, it makes careful comparison even more important here. The camera returns underground, where the same stalagmite still catches drops from the ceiling above slowly. What looked like a quiet sculpture is really an ongoing experiment shaped by the world above. Every new drop may carry traces of today's soil, rainfall, vegetation, and human activity above us. The archive is not finished, and future scientists may read the years we are living now. But an archive this delicate can be damaged long before anyone learns what it truly contains. A single careless step can crush sediment that remained undisturbed through centuries of darkness below ground. A touched formation may stop growing correctly because skin oils change the mineral surface directly forever. Even a bright trail light can alter the small living communities clinging to damp stone walls. The deeper lesson is simple: reading caves also means protecting the conditions that preserve them well. As the lab lights fade, the story returns to the cave entrance and the surface above. The next threat begins outside, where rainwater runs across pavement before disappearing into limestone cracks below. What enters the ground can travel farther than people expect, through routes no map fully shows. A parking lot, farm field, or neighborhood can influence water that later drips inside a cave. The cave may feel remote, but its chemistry can begin beside a road after rainstorms nearby. Pollution does not need a dramatic spill. Small, repeated traces can slowly change underground water chemistry. A muddy footprint on a protected floor can blur evidence older than many American towns nearby. Broken formations reveal a harsh truth: thousands of years of growth can vanish in seconds forever. Conservation signs are not decoration, they protect records that cannot simply be rebuilt by people later. The camera passes a locked gate, showing protection not as fear, but as shared responsibility today. Beyond the gate, darkness continues recording, while the surface keeps deciding what the archive receives next. A touched cave formation may look unchanged, yet its growing surface can be quietly altered by human contact. Skin oils and repeated contact can interrupt the delicate chemistry that lets mineral layers keep forming. Each growing surface depends on a slow balance between water, minerals, cave air, and patient time. A few seconds of careless touch can disturb a surface that may have grown for centuries. That is why many caves guide visitors along marked paths, protecting records hidden just beyond reach. Even a muddy footprint can disturb sediment layers that might contain older environmental clues beneath the surface. Tourism is not the problem by itself. Careless movement across fragile surfaces can be the real threat. A well-designed trail lets people witness the archive without walking directly through its most vulnerable pages. Some passages stay closed because their records are still too fragile or still being carefully studied. At At the edge of protection, water keeps moving, carrying the surface toward darkness again below us. Rainwater begins above ground, collecting dust, soil, pavement residue, and tiny chemical traces along the way. In karst country, that runoff can enter cracks and sinkholes far faster than most people expect. Beneath a familiar neighborhood, water may follow routes that no ordinary road map can show clearly. Inside the cave, an underground stream may carry signals from storms many miles away above the surface. Researchers sometimes trace hidden water paths to understand where an entire cave system is connected underground. A small bottle of cave water can reveal what the underground system has been receiving lately. The chamber may feel remote, yet its water can be tied to a town above it. Karst landscapes route water differently, sending rainfall through openings that ordinary drainage often misses completely underground. That hidden speed means contamination can spread underground before anyone sees a warning sign above ground. If caves record ancient climates, could they also record the chemistry of modern life above them? A cave gate may look like exclusion, but often it is a shield for fragile history. Researchers move slowly because every bootstep, breath, and sample can change a small part of the record. Tiny sensors watch the cave's conditions, measuring subtle change without touching the stone itself directly. Temperature, humidity, and carbon dioxide all help shape how minerals grow underground over long periods slowly. Protecting the archive also protects the creatures that depend on darkness staying stable and undisturbed below. Sometimes the wisest conservation choice is not intervention, but simply leaving the chamber alone for decades. A roped-off patch of floor can protect evidence far larger than the space itself preserves below. Where surfaces remain untouched, new mineral films can keep forming over older layers below them slowly. Conservation keeps future questions possible, including questions scientists have not yet learned to ask clearly yet. The story now turns from what we protect to what the cave is recording today underground. Modern droplets still fall on ancient surfaces, adding thin new layers to older stone below them. The chemistry in today's water may become a signal for scientists in the future underground. A layer thinner than paint can connect one storm to a timeline thousands of years long. We are not standing outside the archive. In small ways, we are entering it today too. A visitor's path, a research sample, and a storm above can all leave consequences below. In a protected chamber, the cave continues recording without drama, noise, or visible urgency over time. Scientists read these records by comparing layers, dates, chemistry, and the cave's wider context carefully. When context is disturbed, even an old clue can become harder to understand later on clearly. Future cave records may reveal not only climate, but how carefully we treated darkness below ground. The warning fades into a quieter question, carried by the same falling water below us now. A fresh mineral film spreads across ancient layers, adding the newest page to stone today below. The cave is ancient, but its most recent record is being written right now below us. What is this quiet chamber recording about the world passing above it today, right now below? One modern drop belongs to a much longer timeline, stretching far beyond human memory underground today. The cave appears still, yet slow processes continue on ceilings, walls, floors, and pools below us. A human figure becomes small inside a record older than any family story remembered today underground. Layered stone links vanished climates, recent storms, and the present beat of water below us now. A cave record grows through repeated small events, not one dramatic moment of history alone ever. Rain falling today may leave a future signal in stone no one has read yet below. As water descends again, the final question follows it into the cave's future memory below. The same drip line glows in darkness, carrying the surface storm into a place that seems completely still. Water does not simply fall into a cave. It travels through cracks, carrying traces from above. A cave record begins with repetition, as small chemical changes settle into stone over long periods. One fresh wet line becomes tiny beside the stalagmite, yet it belongs to a much longer timeline. The cave is not cut off from the surface. It receives signals, then protects them from erasure. Fresh calcite spreads over older bands, placing a new layer on top of a much older memory. A human observer stands briefly before stone that has been forming longer than any living memory. Along the wall, mineral bands resemble pages, but scientists must still learn how to read them. What forms today may become evidence later if future scientists can separate real signal from noise. The droplet fades into a pool, and the cave widens from one formation into a whole system. In the dark water, stone, sediment, and reflection gather into one quiet underground record together below. The floor holds its own archive, where mud can settle in layers separate from growing stone. A small trace in sediment means little alone until its position and surrounding layers are understood. Cave evidence becomes useful only when context, dating, chemistry, and comparison point in the same direction. Even here, life moves through the record, changing the present while the older past remains nearby. A cave is not a frozen museum. It preserves history while slow living systems continue changing. From floor mud to ceiling drip, the archive stretches through the entire chamber around us today. Caves preserve best when they are connected enough to receive signals, yet sheltered enough to protect them. What we protect now may decide how clearly the next generation can read these underground records. As human light fades, the cave returns to its slower work of receiving and preserving signals. The final chamber appears motionless, but every small drip proves the archive is still active tonight. A droplet slowly gathers minerals from its journey, carrying more than water toward the formation below. Chemistry, water, time, and shelter combine here, building an underground record too slow to watch directly. The smallest repeated action can outlast us forever, becoming evidence long after the moment has disappeared. Old bands, fresh film, and falling water quietly meet in one frame, turning stone into memory. People eventually leave the cave, but the dripping continues alone, writing without witnesses in the dark. Above ground, time feels fast and noisy. Below, it narrows into patient underground mineral change slowly. If this newest layer could speak someday, what would it reveal about the world above us? The present falls towards stone, becoming part of a record no one can finish reading yet. One drop joins the surface, spreads across mineral, and leaves the cave quietly writing in darkness.